Welcome to the lecture on orthogonality. We are going to learn about establishing whether or not vectors in CM are orthogonal to each other. And that requires that we have to develop a number of tools. Before we continue, I would like to remind you that if you haven't done so, you should make sure that you're up to date with what is called complex number operations. Okay, complex number operations, complex number CNO. Complex number operations are going to be fundamental for some of the things we are going to define in this lecture. Okay, and we start with an operation that's called conjugation. The conjugate of a complex number is something that is inherited or propagated for vectors that are column vectors that are defined in the vector space CM. Okay, so the so-called conjugate of a vector is defined with the same type of notation. See this little bar here on top of the vector denotes the conjugate of a vector, and we're assuming that a vector, what we're writing here is that U is a member of CM. So U has several entries, right? So U has U1, U2, this is U here, being a column vector, has U1, U2, U3, all the way to U sub M, right? It has M entries. And so we say that the conjugate of a vector is a vector itself, a member of CM, such that the kth entry of this new vector, the kth entry, is the conjugate of the kth entry of the original vector, right? So this seems rather intuitive. If this is the vector, we're saying, well, then the U conjugate is going to be another vector such that the first entry of this vector is the conjugate of the first entry of U, the second entry is the conjugate of the second entry, and so on and so forth until we go through the very last entry, and that entry is the conjugate of U sub M, right? So this would be a way of expressing what is expressed here in symbols for every index k between 1 and m. Now, just because, just precisely as an implication of the properties of conjugates of complex numbers, it turns out that when you take the conjugate of the sum, that at the level of scalars, then that becomes the sum of conjugates. Well, if you're considering vectors, that property is preserved. So if we have two members of CM, so here we're saying that X is a member of CM and Y is also a member of CM, then the vector X plus Y is also a member of CN because of closure and their addition. And the sum, being a member of CM, has the property that the conjugate of this vector is equal to the conjugate of X added to the conjugate of Y. This is something very straightforward from properties of complex numbers. The other thing here to keep in mind has to do with multiplication. Multiplication of a scalar alpha, a multiplication of a scalar alpha with a vector in CM, right? So this alpha x is something that looks like here's the scalar and here's the column vector, right? So that operation is a column vector on its own, right? But here we're saying if you consider the conjugate of the scalar vector multiplication alpha x, that is equal to multiplying the conjugate of alpha, which is a scalar. So here on the left side you have scalar times column vector, and that is equivalent to multiply the conjugate of alpha, also a scalar, times the conjugate of x, which is a vector, right? So these two things are going to end up being a vector of length m, m entries. Now, we have involved the operation of conjugate so far, and we're going to involve it even a little more into an operator that's called the inner product. Okay, this operator, inner product, it's something, if you want to write it as an operator, the inner product is going to have a notation that looks a little bit like the span of a vector, okay, but it's not the span. In this case, it has two arguments, which I'm writing here in blank. Okay, each of these arguments is going to be a vector. The vectors have to have equal length, so they have to be both vectors of CM. And as an operator, we're going to say this is an operator that takes arguments in CM, two of them. So we say CM cross CM. Okay, so that means that you need to take two arguments, each of which is in CM, and we write an arrow, and this gets mapped into C1, basically, C1. It means two column vectors with complex entries go into the so-called inner product, and then a complex number comes out of that inner product. Okay, and so the way that is defined is by involving the entries of these input arguments u and v, and you will see in just 1 second, involves those entries. It in fact involves the conjugate of one of these vectors. So here's the notation. This inner product is precisely this operator. Okay, see where there's this symbol here that looks very similar to the span of a set, but there are two things, two arguments, u comma v. That means there are two arguments, and that is defined as a summation. Here a lot of things are being added up. So here's the first term, here's the second term, here's term number 3, etc., until you have term m, okay, in position m. And how do we know that? Well, we're assuming that both of these column vectors have m entries. They have to have the same number of entries so that this summation works out. So we're multiplying element by element, location by location, both elements in entry 1, both elements in location 2, and all the way through both elements in location m. But you need to be very peculiar here. So we're multiplying. So this involves the conjugate, right? This involves the conjugate of the entry in the vector u, being the vector that appears first here as an argument, and also involves the entry, not the conjugate, but just simply the entry of the vector that appears second in the argument. That's what's happening in every single term of the summation. So we can write the summation in short with this summation notation, right? And so here we're saying we have a vector that appears first that we called u, and that is the vector that that the elements, the entries of that vector are conjugated, and the conjugate of each entry is multiplied by the corresponding entry of the vector that appears second. Okay, the vector that appears second, which we're calling here v. So in essence, we are trying to match entries of both vectors, and we are multiplying those entries with the caveat that in one of those locations, for one of the vectors, the vector that appears first, we have to take the conjugate. Okay, so everything is always, well, not everything, but some things are best digested if we have concrete examples at hand. So here we have a given vector that we're calling u, and if we want to compute u conjugate, that means we would take the conjugate of every entry. So this would be 2 minus 3i for the first entry, 5 minus 2i for entry number 2, and then minus 3 minus I for the third entry. This would be the conjugate of u. Given that this vector is u, this would be the conjugate of u. Okay, and so those entries, 2 minus 3i, 5 minus 2i, minus 3 minus I, would be the entries that we would employ in the calculation of inner product, right? So here we have this here is going to be the inner product of u and v in that order. The order of this operator matters. So u comes first. Okay, so let's see how this works out. Because u is listed first, so the first thing that we do is here we're listing the conjugate of u1, and this would be denoting the conjugate of the second entry, and this denotes the conjugate of u3. Okay, so if we calculate those terms, conjugate of 2 plus 3i is 2 minus 3i, as we had pointed out, and then this term, conjugate of 5 plus 2i, that becomes the complex number 5 minus 2i, and the next calculation involves minus 3 plus I, the conjugate of which is minus 3 minus I. So once we do that step, then we proceed to do the algebra, which is basically multiplication of complex numbers and summation or addition of complex numbers. So that means that we're going to say 2, for example, in the first term here, 2 times 1, 2 times 2i, minus 3 times 1, minus 3 times 2i. And doing that calculation, maybe I'll do the first calculation. So here slowly, so 2 times 1, let's see, that will be 2. 2 times 2i, that will be 4i. Minus 3i times 1 is minus 3i. And minus 3i times 2i would be, minus 6i squared. Right, so here's where you have to be very careful. Remember the definition of I being square root of -1, which implies that I squared is -1. Okay, and so that this I squared is a -1, which is multiplying a -1. So this becomes 2 plus 6, and then we can add these two terms, which are adding up to be 1i. So this becomes 8 plus 1i, okay, which is what we have in the next slide. So this product, the multiplying these two complex numbers, gives us 8 plus I, multiplying these complex numbers gives us minus 10 plus 33i, and the multiplication of these two complex numbers yields 5 minus 15i. So I worked out the steps, intermediate steps for the first multiplication. That's why I remind you that you have to be current here with complex number operations. You can pause the video and carry out these calculations and make sure that you're up to speed. This would, remember, once we carry on with these multiplications, then we move on to add similar terms. So we are adding all real parts. All real parts are added up, and all imaginary parts are added up. And so this inner product between this vector u and this vector v, this inner product becomes 3 plus 19i.